Hello, and welcome to Lecture 5 of the Work Unit in Phys 1104. Up until now in this unit I've been sticking very definitely to one-dimensional cases, but now it's time to generalize that to two dimensions. Remember that for a constant non-dissipative force acting on a particle in one dimension, the work was just the product of the x component of the force and the x component of the force displacement vector. And this is strictly only valid for a force acting on a particle, but it's a good approximation for the work by a force on a rigid object. And we're specifying f sub x, and in fact delta x sub f, because these are vector components, but we're talking about the case here where the vectors are parallel, so the only possibility is that those components are either positive or negative. But what if the force and the force displacement do not point parallel? Then how do we calculate the work by this force? So let's now think about the case where an object moves through some displacement, delta r, and that's the same as the force displacement vector, delta rf. And among the other forces that might be acting on this object, there's a force we're interested in, which is doing work, and it's oriented at an angle phi relative to the force displacement vector. To think of this, we're going to think of one of the simplest cases we can come up with, a cart on a sloped track, and that's because the forces are all constant, and they are acting in constant directions relative to the motion, and it's a nice simple situation that could in principle be set up in the lab. So we're dealing with negligible friction, and our system is going to be only the cart, and I want to emphasize that the Earth is not in the system. So any effect on the cart by the gravitational force is going to be treated as external work, not as a change in gravitational potential energy. And we can approximate this cart as a particle. In other words, the kinetic energy is the only type of energy in the system. And so our energy bar chart just looks like this, where I've said that initially it's at rest, so Ki is 0, and there's external work done, resulting in some non-zero kinetic energy later. And the work, by definition, is just the change in the energy of the system, and that's just the change in the kinetic energy. And in particular, just for simplicity, we don't need to do this, but it's going to make things simpler. I'm going to start the cart from rest, and so the work is just going to equal the kinetic energy at the end. So we have a nice simple free body diagram with only two forces on it. And I want to point out there is no possible change in the system's internal energy. We're treating this as a particle, and so the only energy is kinetic energy. There's no internal energy. And the only external state change happening is the change in the relative position of the cart and the Earth. And so that means that all of the work done must be done by the gravitational force. The perpendicular force due to the surface is not doing any work. And so we've identified a situation where we know exactly what force is doing the work. It's the gravitational force. And note that it isn't parallel to the motion. Now, normally when we talk about things on slopes, we tend to talk about the angle of the slope from the horizontal. But here that's not actually the angle we want to work in terms of, because remember that we want to work in terms of an angle, which is defined as the angle between the force and the force displacement vector. And so in particular, we want the angle between the gravitational force, which is the only force doing work here, and the force displacement vector. And that is the angle phi indicated in the diagram. So I'm going to decompose the gravitational force into its components parallel and perpendicular to the slope, and I'm going to work in terms of that angle phi that I've just defined. And so I drop my perpendiculars, and I will label those. You can see what I'm labeling as the x and y components, and there is my angle phi. And looking at the triangle, you can see that the x component, which is the one we're going to be interested in, is the adjacent angle to that angle phi. And so we can say that it is just the magnitude of this gravitational force times cos of phi. Or in other words, it's mg cos phi, where I'm emphasizing that with my choice of axes, that's positive. So My acceleration is just in the x direction, is just all the forces in the x direction over the inertia, but that is just that component of the gravitational force. And so all I get is g cos phi for the acceleration in the x direction, which is the whole acceleration. We're almost finished. We just have some kinematics to do, but I want you to keep your eye on the prize because these arguments are getting a little complicated. Remember that all we're after here is the work. We want to know the work done by this force that is not parallel to the motion, and we've seen that I've set it up so that that's going to be equal to the final kinetic energy. So now I want you to note that the force displacement vector RF has a magnitude that we would just call delta RF, and that is equal to the x component of the displacement of the cart. And so that's going to be useful as we go through the kinematics. All we have left to do is a little bit of kinematics so that we can write an expression for the final kinetic energy. And so this is uniformly accelerated motion, and I've written one of our old friends, the uniformly accelerated motion equation number 1 here, and I've noted that we started with an initial velocity of 0, and we know ax, it's g cos phi, and so we can write the final x component of the velocity like so. Our second UAM equation is right here. And again, I've said that we've set our initial velocity to 0, and so I can solve this for delta t, or rather delta t squared, and get this expression, which is going to be handy in a moment. So now we have all we need to write what we're after, which is the work, which after all is the final kinetic energy. So I can just write down my final kinetic energy. As always, it's going to be a half mvf squared. And since the cart is moving directly in the x direction, its speed is the same as its x component of velocity, or rather once it's squared it is, since there could be a negative in there, but that's now gone. Okay, but I know vfx. I can write it just as ax delta t, and so that's all squared, and so I'll have ax squared delta t squared, and I have this expression for delta t, and so I can put that in, and there's a little bit of cancellation that happens, and what I have is that my final kinetic energy is just max delta x. And I know ax, it's g cos phi. I'm just going to note that what I've just shown is that kf is mg, which is simply the magnitude of this force, delta x, which is the magnitude of the force displacement vector, times cos phi, where phi is the angle between this force and this force displacement vector. And so that is the work done by this force, which was acting at an angle phi to the direction of motion. So we've seen that for a gravitational force acting at an angle phi to the direction of motion, we get a work that's given by this equation, where by Fg I mean the magnitude of the gravitational force, and this delta Rf is the magnitude of the force displacement, so those are both positive by definition. And this angle phi is the angle between the force vector and the force displacement vector. But notice that in that whole derivation, I really only used definitions of angles and arguments to do with uniformly accelerated motion. And so for any constant force acting at an angle phi to the direction of motion, the work should just be the magnitude of the force times the magnitude of the force displacement vector times the cosine of the angle between them. Note that if you just group the multiplications differently, you can think of this as f cos phi times delta Rf, and in that case you can see that it's just the magnitude of the force displacement, delta Rf, multiplied by the component of the force that is parallel to the force displacement. You could also regroup it to think of it as the magnitude of the force times the component of the force displacement that's parallel to the force. I'll leave you to draw a picture of that. But the other thing to notice is that both of these F and delta RFs are magnitudes, and so they're positive. And so now the sign of the work is determined entirely by the size of that angle phi. If phi is acute, if it's less than 90 degrees, then the work is positive. And if the angle is greater than 90 degrees, then the work is negative. And so this agrees with what we've already seen. If the force is in the same direction as delta RF, in other words, if phi is 0, then we get a positive work. And if the force is in the opposite direction to delta RF, then we get a negative work. This work expression that we've got is an example of an operation between two vectors that we haven't seen before. We know how to add and subtract vectors and how to multiply vectors by scalars, but what we're actually seeing here is a type of multiplication of two vectors, and it's called the scalar product. When we write for any two vectors, a and b, a dot b, then we define that as the magnitude of a times the magnitude of b times the cosine of the angle between them. This is called the scalar product. It's also often known as the dot product. That's actually the name you'll hear me use for it more often. And note that the scalar product is called the scalar product because when we take the scalar product of two vectors, we get a result that is a scalar. And so looking back at our expression for work, we can see that we can just write it as the scalar product, or dot product, of the force vector with the force displacement vector. Well, that's the work due to a constant force, but let's generalize to a non-constant force. Just as we did for forces and displacements in one dimension, we can generalize this, and it's going to end up as an integral. The integral probably looks a little scary to you, because now we're talking about general displacement vectors that can be pointing in any direction, dotted with force vectors that can be pointing in any direction and which depend on the position. So that looks pretty scary, and by and large I'm going to leave further use of this until Phys 1204, by which time you'll be more comfortable with integrals, but I am going to show you a quick example of how to use this to think about a work done by a force. Let me first just show you that there's another way of understanding this work done by the gravitational force in this case. So notice that this angle phi between the force and the force displacement is the same as this angle phi right here. And that tells us that this h is just the magnitude of the force displacement vector times the cosine of phi. But that's right here. And so that means this is h, and this force magnitude is just mg. And so I can write that the work done by the gravitational force here is just mgh. So now I can think about a cart going down any shape of curve. And so I can divide its motion into a bunch of small displacement vectors. And each of those corresponds to some change of height. And so I can think of the work done by gravity on each of these as just the gravitational force dotted with that little displacement vector, and the total work is approximately just the sum of all of those. And note that what we've just seen is that is going to be the sum of all of the mg hi's, where hi is just the height of the ith little piece of path. But that means if we take the limit as our delta r's go to 0, then we're going to just get a sum over all the, an integral rather, over all the mg little h's. And that's just mgh, where h is the total height that the cart goes down through.